Hello everyone, it's July the 1st. We're entering a new month. Alright, excited. Let's see what we have today. We have a notification, probably nothing of concern. Oh, asking me to join a weekly contest. Maybe I should join a weekly contest someday. But it's too late. It's 10, I think it's 10:30. No, it's 10 o'clock. 10 o'clock Saturday night. And it'll end at 11:30 p.m. It's too late. My brain's already toasted by then. All right, let's do this. Gray code. An n-bit gray code sequence is a sequence of 2 to the n integers where every integer is in the inclusive range, blah and blah. The first integer is 0. An integer appears no more than once. The binary representation of every pair of adjacent integers differs by exactly 1 bit, and the binary representation of the first and the last integers differs by exactly 1 bit. Given an integer n, return any valid n-bit gray code sequence. Ooh. N, the range all the way to 16. So we can use some pretty dumb ways. I think we can still pass this. All right, let's see. What's a binary representation of 0, 1, 3, 2? Given value is 2. So we have 2 to the 2 is 4 minus 1 is 3. So 0 to 3. And I have seen this in class, the gray code. Yeah, I have seen this before. I think it's used in to detect if there's any corruption in the transmitted bits. So you can compare adjacent. If the adjacent differs more than 1 bit, then you know there is corruption. Yeah, I think this is for the corruption detection, or what's it called? The integrity test, something like that. All right, so I have 2 different versions for this. Okay, but the numbers could be huge. Oh, the binary, it's not huge, 16. So it's the 16-bit, right? So at most, we have 2 to the 16 minus 1. Is that 15 bits or 16 bits? It's 16 bits, right? No, it's 2. That's 2 bit. Yeah, that's 16 bits. So we can just lay out 16 bits, right? That's fine. We lay out 16 bits, and then we can do what? Bitmap. Every number is different. We just need to arrange the number, right? Arrange the number such that every adjacent is differ by only 1. Okay, let's see. So given n, we know how many bits, right? We know how many bits. So can we design it? Like we have a 0, right? And then because we have a 0 at the beginning, so the next one we can design, we say we multiply by 1. Let's see. Let's say n equals 3. Let's see if we can get n equals 3. So we're 0, 0, 0, right? And then let's say differ by 1. And next one differ by 1. And next one differ by 1. And next one differ by 1. So we're adding 1 to the left, so we're moving 1 from, so we differ by 1. Right, and then differ by 1. 1, 2, 3, 4, 5, 6. I think 2 we're missing. Yeah, we are missing. We're missing 1, 0, 1. And 0, 1, 0. right? We're missing these two. So we can do 0, 1, 0. All right, and then hold on. So we have 2-bit, right? That's a 2-bit, 0, 0, 0, 1, 1, 1, 1, 0. So these are the 2 bits, right? 2 bits we satisfy. And then we just turn this, and then it's gonna be 1 bit. We just turn it the other way around. 1, 0, 0. That's it. 1, 2, 3, 4, 5, 6, 7, 8. That's 8. I think we got it. So yeah, we can also go from 0, 1, right? 0, 1, and then we need to add. So it be 0, 0, right? We need to add 1 to it. So we keep 1, 1, and 1, 0, and then we do this. Basically, we do a mirror image, right? We do a mirror image, and then we add a 0 at the front, 1 at the front, and this whole thing we do a mirror image. Okay, got it. How do we implement it? How do we implement? And then this thing actually, we think we can create like a library. All right, we're gonna create a library because only 16. How do we implement this thing? So we have 1. We know 1. We can get 0, 1. And we know 2. Oh, hold on. So basically we just add 2 to the n minus 1 to it, right? And that shall be right. Okay. Okay, hold on. So we have the original, and then we just reverse the original. We add the new number to it. Okay, let's do this. Yep, I think this is the solution. Oh, hold on. We have to create a new folder, right? So 7 challenge. And I'm gonna copy into July the 1st, and we're gonna open July the 1st. There we go. That's the one. Hold on. Layout symbol. Yeah, I think what I'm going to do is using the LeetCode trick. So we can create something as a persistent variable inside solution, and then we can call it in here. So we can say, what do we say? We can just like def, right? And then initiate self, right? And then we can create, say, self dot result. That's going to be a list, right? A list, yeah. And then we can say 0 is this, 1, we already know 1's what? 1 is 0, 1, right? 1 is 0, 1. And then we're going to say for I in range, so from 2. Oh, actually we can do 0. We can do 0, right? And then we're going to say from 1 to 17. Right, each one, we're going to go template is equal to self res I minus 1. Right, that's a template. When we get that, we need to reverse the template and attach to it. So we can say temp equals plus equal temp reverse, and we're also gonna add the thing to it. How do we handle that? I think we can do this, right? Temp and then we say addition, right? Add on, right? Add on. For the add on equals 2 to the I minus 1 power. And then this will be add on plus t for t in this. And we can direct say self.res.append, right? When append temp plus this, right? So we're done. That's it. That's how we handle. And then we want to return self.res n. All right, I'm gonna run some test case on this. The test case, we're gonna start with n is 2. Result is 0, 1, 3, 2. 0, 1, 3, 2, right? Next one is 1, 0, 1. Yeah, pretty weak test cases are these two actually, but it doesn't really matter. Just want to see if this one is correct. Gray code n, right? Both pass. Yeah, I think this is the one. We can do another one. Let's do 16, right? Let's do 16. Let's see what will happen. Yeah, I think that's the same, right? I think that's the same. All right, submit. Pending. Judging. Accepted. Yep. So the idea is that for to compute, right, to obtain the gray code for n, we look at the gray code of n minus 1. All we need to do is to reverse the gray code of n minus 1 and add 2 to the n minus 1 to each value in the reversed gray code. Then we concatenate the two arrays and we have the new gray code for n. So the runtime is it depends on how you define the runtime, right? The runtime for each n, we have to compute the previous ones. Right? We have to compute everything the previous. So if we just look at every time, then the runtime is, for each one, we have to go n times. Yeah, for 1, we have to go 1 time. For 2, we have to go 2 times. So it should be O(n) squared. I think it's O(n) squared, right? O(n) squared. But if we do this, then it's basically O(1), right? If we compute each gray code from scratch, we can also do one computation at the beginning, and then store the result, which will make oh, let's see, what is our runtime? Oh, it's slow. I thought it would make it faster. This one is 144 milliseconds. Let's give us 28% ranking. Does that mean there is a better option? I think probably there's a better option. Let's see. Bit. So instead of doing this, I think they use a bit maneuver. How? Wait, you have two gray code. Which one? Total. Answers are append. There's a different. I think this one maybe we can do it like, wait, instead of reversing it. Hold up. For every one, answers are append I, exclusive OR, I, right shift 1. So we have a current value, no matter what value it is. We're going to right shift 1. So right shift 1 will be this, and we exclusive all these two. So myself, exclusive all, myself, right shift 1. That's correct. If I right shift 1, then, because if I exclusive for myself is going to be 0. But if I right shift 1, what's going to happen when I right shift 1? Then same will still be 0. Like if it's the same, if right shift 1 will cause indifference. The difference will result in 1. But because I right shift 1, there should be only one difference. Right? There should be only one difference. No, it shouldn't be like one. Hold on. How do you right shift 0, 1, 1, 0? 1, 0, 1, 1. Wait, how is this correct? Right shift exclusive all. We have two differences. Hold on. I don't understand this. I right shift 1. I have 2 bits different. How is this correct? I missed something? Should be a 1, 0. Let's see. I'm a bit confused. I think it has a solution. This might be an easy question. A medium. Oh, I've done this before. 89. Last time I done this is last year. No, 2 years ago. July 16th, 2019. And I scored a very high with 44 milliseconds. But today I got it 144. Well, what the hell happened? I scored 44 milliseconds. I'm computing every single one. I don't understand my solution. Let's take a look at the last one. I think this is probably the one. Okay. X or X in res. This is the same. For X, yeah, in res, we reverse it. Yeah, we reverse the res. And then for each one, yeah, that's the same. It's the same as this one. But this runs faster. I thought this one would be faster. Maybe they call a new solution every single time. I think that's probably it. They call the new solution every single time. Let me try it again. It shouldn't be, because from my experience, they only call solution once, and then they just call solution dot something, solution dot something. Yeah, what this shows me is we don't have to do this, right? And same solution, but compute from scratch each time. Let's just see. So we can call res as this, and then for I in range 1 to plus 1, right? And then we say, actually we don't have to, we just can say res is 0, right? And then for this, and then we say res plus equal to, yeah, for R in res reverse, and we're gonna say, what? Let's say R, or bless you. That was very good. It was a very, the sound is very good falsetto. 1 shift to the left I times, right? And we return res. I shall do it. Nope. It's not correct. How 0, 1 becomes 0, 2? Huh. Oh, it should be like I minus 1 times? Oh yeah, it's I minus 1 time. Which just means we just go to n then. There we go. Yeah, maybe this is faster. I mean, this is the same solution as last time. There we go. Faster, 96 milliseconds. They did. I think they increased the test case size. So this one's 96 milliseconds, or a 96% ranking. So my hypothesis is wrong. They do call solution every single time, I think. Huh. Okay, let's go to the solutions. Backtracking. Recursion. Iteration. It's 2 to the n. Come on, it's 2 to the n, not n on n squared. It's 2 to the n. So you have to calculate every single time. Oh yeah, it's 2 to the n. 2 to the n. Come on. Not o n squared. It's 2 to the n. Alright, I think this one is what we have. We got the intuition here. Oh, it's recursion too. Oh my god. So many. Oh, iteration with a single loop. What? Wow. Yeah, this is, I think, the one. What is the recursion idea? So backtracking, the adjacent number and sequence should differ by only 1 bit. And so we know that Recursion sequence always starts with 0. As a brute force solution, we can start a depth first search from the number 0. So again, we'll try all possibilities. All possibilities for 0 that can end up with 1. bit difference, and we keep going. And if it fails, we backtrack to before, and we keep tracking something. We keep trying something different. Okay, so no, that's not the way that we're going to go. All right, so I think this is the helper. All right, so we're going to say next equals current. Do this. 1 shift left I times. What does one do? Is present or find next? Erase next and pop. Order set is present. Is present or insert 0? Okay, 0 is present. And gray code it. If result.size equals this, then true. Yeah. Current value is result.size minus 1. Yeah. And then the next value. So this one, current value exclusive OR. At each position, right? We can let's modify each position. Yes, modify each position. We go for 1. If it's 1, it can be yes. So next is this, and then if it's this means that's an order set. That means the set is not in it. Then we insert it to it. Result push to it. Keep going. If it's true, we turn true. If not, we erase it. We pop it. Okay. Yep. That's correct. Recursion. Isn't backtracking is recursion? Come on. So 0 to 3. 0, 0 for 1 is this, and we have this. By observing the sequence generated, we will find a pattern. We can obtain a gray code sequence for n from the gray code n-1. Yes, we can, and then it's not necessary to use recursion to do this. Iteration. Iteratively. Mask, yeah. Pushback, mask plus this. Isn't that the same as not recursion 2? But this is the same as with a single loop. This is a single loop. Oh, hold on, this is 2 loops. Wait, how is this 2 loops? So for the loop, and then I get a mask, okay? And then for the result, I'll push back, result, and come up and find out. This is a 2 loop too, 4 and 4. Okay, so this is a 2 loop. These two are the same solution. And I'll have another recursion. No, we're not going to do recursion. Come on. But we're going to read it. So we'll have a result. If, what's n? N is 0. We're going to push back next num. The next num is changing. Return. Otherwise, we call helper result n-1. So keep going until the end. Then we push back the num. Coming back, we're going to flip the bit and n-1th position from the right. And then we're going to call, after we flip it, then we're going to call n-1 again. So we call this already. After we call, we change the next num, and then we call this one again. huh. And after we call that, we go to the front, then we change. So all we're saying is we always change n-1th position from the right. We do it, going back front, we do it. So we go leaf node, right? Leaf node, then we change this, and then come here, we change this, and then we change the front. I seem to know what this is trying to do. So we go down, coming back. So 0th bit from right. The 0th bit from right, because it's n-1, right? So 1 minus 1. So 0th bit from right. And we'll do it again, and then come in, and then we're done. So go here. So we're gonna do 1 bit from the right. So we're gonna change this to 1, and then we're gonna keep pushing n-1. Hold on. So n is this, and push, and we're done. Now we change this. We change this, and then we're gonna change the last two. So we do this. We change the last two, and then we change this one, and then we go in here again. Yep. I don't think I'll implement that one. It's not happening. All right, so that's one loop. Oh. I shift once. All right, so that's the solution that I was confused earlier. I have a proof. Single loop to calculate all. Without prior knowledge, we have included here for completeness. It's optimal in terms of the overall complexity. By comparing the input values to the expected output values, we can identify the pattern of a relationship between the two that allows us to calculate the output values in a more efficient way. We first need to solve the problem using one of the previously discussed, more intuitive approach and search for a pattern. Take a minute to look at the table provided. Can you spot the relation between index I and a great value gi? So the difference is I index exclusive or gi has 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. Take the exclusive OR of I and gi. Now that I and gi always equals I divided by 2. Yes. Floor division, that's true. We see that gi is equal to I exclusive OR. Hold on, so we say this equals this. I exclusive or gi equals I divided by 2. Therefore, gi equals I exclusive OR. What's the rule for exclusive OR? Because I exclusive OR I is going to be 0, right? 0 exclusive j. So we just put I exclusive in the front. That's equivalent to now in the proof, We can do, I think we can use induction to prove this. We need to prove gi and gi plus 1 differ by exactly 1 bit. This and this. Exclusive of all is commutative, so we can take out all the parentheses, and then we can combine, recombine. Hold on. We just swap things around, right? Exclusive of this, exclusive of I. Wait, what happened to this one? What happened to I exclusive of I this? And we have another I. I don't understand this part. I right shift 1. Like this one is gone. This part is gone. Okay, I know it's commutative. This one's still here. I have I do this. I have I plus 1 here. And I goes, I don't know. What is it supposed to mean? I right shift 1 and exclusive or I plus 1. I don't know. I right shift 1. Why is this able to be cancelled? Or I plus 1 right shift 1. Oh, hold on. I plus 1 right shift 1. Is that like equal to I right shift 1? Not really. Depends. It depends. Alright, let's read. Adding 1 to any number is equivalent to toggling every bit from the rightmost 0 bit to the end. The 0th to the 3rd bits are flipped, or the other bits remain the same. Thus, in general, if I equals I plus 1 will be this. First bit to the left remain than any sequence of binary bits. So we have observed the length of the tailing 1 bits of I will be the same as the length of the tailing 0 bits. The bits from the beginning up to will remain the same, yeah? After this will be opposite. Exclusive OR product of I and I plus 1 will be the form of, that's true. But how do you come up with this? And it's this, the whole thing, right shift 1. It's like I right shift 1, and I plus 1 right shift 1, and I think exclusive OR is we have exclusive OR this and this, these two together, and as I right shift 1 exclusive OR I plus 1 is equivalent to I and I plus 1 exclusive OR and then right shift 1. Is that correct? So we plus 1, then right shift, then do exclusive OR. Or we exclusive OR first. Exclusive OR first. Oh yeah, that is the same. Okay, so we can do this, and this one will be the shape of 0, 0, 0, 1, 1. And then if we right shift 1, then we just add in one more 0 and a minus 1, 1. And then if we exclusive all these two, then we will definitely have we want them is these two differ by exactly 1 bit. It means if you exclusive all these two, we'll have 1, 1. And that's true. They will only have 1 bit. Yeah. No number is repeated in the sequence. So we just understood this part, and then we have more. No number is repeated in the sequence. Gi is bijective. Gi is equal to j if and only if I equal to j. But gi equals this, gj equals this. If this is two the same, then this equals this, and this equals this, and this. Yes, we have that. That x equals this equals binary representation. X right shift 1 is going to be this. If this equals to this, then this and this equals 0 by doing bitwise comparison. N equals 0, so bn minus 1 equals 0. These two equals hold on. I think this one is not right. This should be bn minus 1. This is bn minus. Hold on. So 0, yeah. So 0 bn minus 1, bn minus 1. This should be minus 1, right? And this should be minus 2. That makes sense because minus 1. This one is 0, so this has to be 0. And this is minus 2, so this is 0. Yeah, that's a 0. All the way down to 0 and 1. We can see it's wrong because this should be a smaller value. This should be a bigger value, right? And this is these two are a little bit wrong, but we know what it's trying to say. So everything is 0. Thus, x equals this equals 0. We can conclude I exclusive of j is 0, so I equals j. Nice, good proof. Good proof. I'm very happy that I went through this. Yep, I like the proof. I like the proof. I mean, there's no reason to really see, but I can leave a comment. So the proof, how do I say? The proof article comment section for questions. Concerns about errors or bugs should be posted on. Oh, LeetCode feedback. What's that? LeetCode feedback. With LeetCode feedback, we're providing a more transparent method for filling content-related issues. Oh, so they're changing the rules. Questions and comment. Concerns about errors. So we can do it here. Create an issue below the types of issues, problem content issues on description, existing test case, solution content, missing solution, solution in a row, submission for any other billing aside to a help center. Oh, hold on. So what do? We go to issues, missing test case, valid sequence does not pass the test, typo in solution. Oh, yep, somebody has already found it. Should be yes. Yes, that's correct. So, give feedback? No. No. So I'm gonna say, yep. So somebody's already found it. So I don't have to do it. All right. So we're gonna code it up. It's very simple, but it does require. Oh, I don't know. I mean, even the proof part took so long. You have to come up with this is pretty difficult. So this is solution 5. Approach 5 in the official solution. It is not easy to find the pattern that GI equals I exclusive or from the pattern that I exclusive or GI equals I divided by 2. I say double divide, so we know what this means. And then the task of proving that GI equals I exclusive or I right shift 1 is also not trivial, but it is a good read. It is a good practice for understanding exclusive or XOR, and also a good read on the proof. So this makes it very easy. So when you say result is going to equal to 0, now I can just go iterate for I in range n, right? We just say res equals, I'm probably going to do this for I in range n, and we'll do what? I exclusive or I do this. And we can return. Solution 3. It's not n, it's 2 to the n. There you go. So it's just one line. Wow. I realized this question can be solved by one line. Yep. Nice. All right, that's it. I think I did a better job than the last time. I don't think last time they went down to approach 5. I don't think they went down to approach 5, but approach 5 definitely is eye-opening. All right, that's it. That's it for today. Good one. I'll see you guys tomorrow. Adios.